Okay, everyone, there are 3 marker pens going around. If you haven't found it, just look around. Somebody has it. Some of you guys, of course, come with pre-made name tags. Stefano over here has his own. Tejas back there has its. I don't know, which class did you make it for?
Data management. No, but it was given to us. So.
It was given to you. Oh gosh. Do you think we can print these out and give them name tags? Actually, no. I think it's more fun when you make your own, right? You can just show me your creativity. And yeah, Stephen is sort of stuck with sitting in the front bench for the rest of the semester because I can't read his name otherwise. It's written in really thin print. Anyway, let's start. I may not invoke you by name, but be prepared for it. Right? Now, this also means that some of you suddenly become names, so I can put names to faces. And now when I see posts on Piazza, I know who made it. All right. We're going to start today with the first of a series of lectures on, as again, everybody keep your laptops shut and phones shut, right? We're going to start today with the first of a series of lectures on training neural networks. There will be 5, maybe 6 lectures. If we go over, we're supposed to be done with this topic by lecture 7, but it might just so happen that we have a guest lecture interfere or that I don't complete the topic. Either way, when that happens, what we will do is record an extra lecture and put it up on YouTube and possibly on Panopto. And you will have to watch that extra lecture because I'm not going to do it in class. And of course, that stuff I don't know in class is what features prominently in the quiz. So it's my way of making sure you watch everything. Now, did you get a sheet of paper? You can write your name on this. So let's start. The class, I may not actually finish all the topics on these slides by the end of the class. If that happens, don't worry. I will catch up with it in the next class. Here's what we're going to be looking at in today's lecture: the problem of learning, the perceptron rule for perceptrons and why you cannot really use it for multilayer perceptrons, the greedy solutions to train networks, and learning through empirical risk minimization, and a brief introduction to function optimization and gradient descent. It gives me great joy to see that I've managed to chase off 2/3 of the class as far as I can make out. All the benches are empty. Now, this of course means that I'm going to start taking roll call in the next class, and we know who's watching the videos. Trust me, we know how long you watched it. We know whether you press the start button and how long you let it run. We also know at what speed you watch the video, right? And so we will be keeping track, and of course, you're not going to get penalized for not watching the video. You're going to get penalized for asking stupid questions that you would not have asked if you had watched the video on Piazza. Okay? Now, so a quick recap. Neural networks are universal function approximators. They can model any Boolean function. They can model any classification boundary. They can model any continuous valued function. We've seen these. Provided, of course, that the network satisfies minimal architecture constraints. We saw in the last class that if it doesn't, then there are things you simply cannot model, right? So in all of these tasks, voice recognition, image text, image captioning, game state, any task at all that you apply neural networks to, you have this box which takes in something, takes an input. What happens? So this, I need to fix this. So it takes an input and produces an output. Guys, can one of you go run up to my office, and there's this big plastic sword. Bring it, okay? So, and these are tasks that can be modeled by neural networks. Question is, I said an image goes in, a caption comes out. Images and captions are not numbers. You obviously need a way of representing it. So how do you represent the input? How do you represent the output? A caption is a string of text. How does a neural network produce a string of text? So these are issues we have to worry about, right? Secondly, once we figure out how these things are represented, the inputs and outputs, how do you compose this box in the middle which computes whatever function it is you're trying to compute? Now, We're going to deal with how to represent inputs and outputs a little later in the coming classes. For today, we will focus on how do you compose the network that performs the requisite function. So again, recap. Here is the basic unit we've been considering all along, the perceptron. It's a simple threshold unit. It takes a weighted combination of it takes a bunch of inputs. It computes a weighted combination and compares this weighted combination to a threshold and fires if the weighted combination exceeds the threshold, and doesn't if it does not. When I say it fires, it means it turns the output onto 1. If the weighted input doesn't exceed the threshold, the output becomes a 0. So we can represent it slightly differently, as we saw in the last class. The inputs, the weighted combination of, instead of comparing the weighted combination of the inputs to a threshold, you can think of it as a weighted sum of inputs plus a bias. Now we mentioned that there's a distinction between these two. In one case, when I just say it's a weighted combination of inputs, what kind of function did I say, combination did I say this was, Joe? This is linear, right? And what happens when I add a bias? What does it become? Affine. And what again is the difference? Does anybody know the formal definition for what it means for a transform or an operator to be linear? Anyone? You good? So we say something is linear if f of ax plus by equals afx plus bfy. That's the definition of linear. And you will find that if I just add a bias, this definition is not satisfied, right? But geometrically, we can also say that if I was to look at this relationship will typically represent a hyperplane in whatever dimensional space where the hyperplane actually goes through origin, right? Now, how do you define an affine function? Anyone? Yes, it's a sheet, but what else? So here's what, when I say something is affine, I'm saying, I assume you can see this. Then I say an f of x is affine. This implies that there exists some c such that I can define g of x as f of x minus c, and g of x is linear. That's our definition of an affine function. But it's all very nice to be formal. What this means in terms of figures is that it's still a hyperplane, but the hyperplane doesn't go through origin. Okay? So this is the basic definition. And so what we are doing over here is computing an affine combination of inputs in the perceptron. So this is the basic perceptron. In the basic perceptron, we looked at a linear combination of inputs and compared it to a threshold. Alternately, you can compute an affine combination of inputs and pass that affine combination through a threshold function, which outputs a 1 if the input is positive and 0 otherwise. These two are strictly equivalent, right? But then once you realize that all you are doing is computing an affine combination and passing it through a function, this function that we will call an activation function, you could replace that activation function with other functions like a sigmoid or those other activation functions that you have at the bottom right. One is the rectified linear unit, the other is the soft plus. They are different variants, but the overall operation still remains the same, right? Now, so one way of representing this, again, when I looked at the bias, when I was looking at the perceptron, I was computing a weighted combination of inputs plus a bias. Now, that made it affine, but then I can also sort of represent it slightly differently. I can say that I can extend the dimensionality of my input, and when I extend the dimensionality of my input, I'm going to add one extra component whose value is always 1 and make the corresponding weight my bias. And in this extended representation, now the combination is just a linear combination. So in many of the figures that we draw on these slides, I will often just not explicitly represent the bias. When that happens, you must sort of imagine that there's this extra input, which is whose value is always 1, that actually just becomes the bias, right? So the structure of the network that we're going to consider is a feed-forward network. And what we mean is that by a feed-forward network is that you have this network of units, and when any input comes in, each unit is going to process that input once, and the signal is going to go out of that unit onto further units downstream. They will not cycle back and come back to the same unit. There are no loops in this figure. So it's a strictly feed-forward network. And part of the design of the network is what is the structure of the network? How many neurons do we have? How are they connected? And so on. For today's lecture, for whatever function we are trying to model, we are going to assume that the architecture of the network, which is the number of neurons and the layers and how they're connected, is actually capable of representing the function, right? So here is what the whole thing looks like now. I've explicitly represented the bias terms over here in this figure. The network is this network of basic units, but overall, what is it really? It takes an input, it computes an explicit output. So the network is a function. It operates on the input and produces an output, a deterministic output for any given input. And the function has parameters. What are the parameters of this function? Anybody? Everything that actually makes the behavior of the function change if you modify it, namely the weights and the biases, right? This is my pointer because my laser is not working. Also, it's more dramatic. Anyway, so when I'm speaking of learning, so the network is a function with parameters that must be set. As we said, the network can approximate or model any function. Now, how do you make it model a function? You have to choose the weights and the biases properly, such that the overall function that results actually models whatever function you're trying to make it represent exactly or as closely as possible, right? So this is what we've seen so far. Let's move on. What we've seen is that the multilayer perceptron can represent any function, but in order to make it represent a specific function, you have to adjust all the weights and the biases to the right values so that it actually represents the function. So how do you actually construct the function? I give you a function, and I want you to compose an MLP that composes this function. How do you actually construct this MLP? One way to do it, of course, is handcrafted. Let's say I want a function that produces a 1 inside this diamond and 0 outside. Then I know how to compute an MLP for this. I'm going to have one perceptron to capture this boundary. In this particular case, the perceptron's weights are going to be 1 and -1. And I can actually write those weights by simple inspection. We'll see how in a few minutes. But so once I do this, there's one perceptron for this, one for this one, one for this one, one for this one. I can combine the lot. I've composed a network which actually computes this function, a function which produces a 1 inside the diamond and 0 outside. Now, this is a very trivial function. I could visualize it. I could inspect it. I can draw my function. I can draw my network, right? The problem is, in all but the most trivial problems of this kind, you can't really do this. Most functions are so hard that you cannot even characterize them. And so what we really need to do is to somehow learn how to model, how to compute these, learn the weights and the biases, the parameters of our network to model the specific function that we wanted to model. So let's say you're given a function g of x, and then you want to learn the parameters that will actually model this function. So you want to learn the parameter. Again, you're assuming that the network is sufficient to model this function, right? So now you want to learn the parameters of this network such that the network actually computes this function. How can you go about it? Now, so just assume for now that I have a scalar input. This is just for illustration. So this is going to be x, and your network is going to be f of x semicolon theta, where theta are the parameters of your function, of your network. Now, if I set my weights and biases to some arbitrary value, then the network is actually going to be giving me some peculiar function of this kind. Now, g of x, the function that I'm trying to model, is going to be a different function. So that function might be, say, this, right? This is g. So what happens is that at each point, this function that my network computes, if I set my weights to any particular value, at each point that the function that the network computes is going to be different from the function that I actually want it to compute. So, and there will be a resulting error, which is this guy, right? So overall, if you look at this region, the area of this region tells you how wrong my network is in modeling whatever function I'm currently trying to model. And so when I set the weights and the biases of the network, what do I want to do? I want to reduce this area down to 0. So the way I would do it, at each point I will come up with some way of quantifying for each x. I'll come up with some way of quantifying this gap between what the function is and what the network actually computes for the current w. And the area over here is going to be just the integral. This area is simply going to be the integral of this function, this quantification, which I will call the divergence, across the entire input space. And what we really want to do is to compute the weights w, so you're doing the argmin over w that minimizes this area, the area of the error between what the network actually computes and what you want it to compute. That makes sense to everybody, right? So this is the problem. But then when I write this equation down, I'm making an assumption. I'm assuming that g of x is known. I'm assuming that I know g of x at every x, and therefore I can compute the gap, the difference between what the network computes and what the function is at every x, and therefore I can compute this area. In practice, g of x will not be specified. So all you will have are going to be some examples. So consider you're captioning images. You do not know a function g of x that's going to give you the caption for every possible image anybody could ever imagine. All you have is, the best you can do is to have some samples. For this x, here is the value I got, I need, right? So at a very specific set of x's, you might have this g of x, right? So all you're going to have is some examples of x, some samples of x, and the corresponding g of x values, right? And based only on these samples, you're going to have to determine the function. So you won't have all of g of x, you won't have the entire mesh. You're just going to have some input-output combinations from g of x. And it is from these input-output combinations that you've got to figure out the network that models all of g of x. Okay? So, and now, these input-output combinations are samples. In real life, they are very easy to obtain. This is just the business of collecting training data. So for example, if I'm building a network to recognize speech, what are my input-output samples? Examples of speech and the corresponding transcriptions. If I'm building a network to caption images, these input-output pairs are just images and their corresponding transcription and so on. The business of collecting these input-output pairs is fairly trivial. We won't bother ourselves with it. The fact that remains is that you don't have the entire function g of x that you want the network to model. You only have input-output relations at a select set of points x. And from these select set of points, you must build a network that computes the entire function g of x everywhere. So we must learn the entire function from just these few samples, the training samples, where for each sample you have the x and the corresponding d, which is the value of the function g that you're trying to compute. So the way we will do it is this. You don't really know what the value of the function is in all of these other regions, right? So you don't have this, guys. You don't have this. You just have these little regions. So what we will do is to try to train the network to fit just these points exactly, because that is all the information you have. You have no more information. And hopefully whatever function that you compute, whatever function the network computes that connects these guys also gets the correct value of G elsewhere. That's the whole paradigm. So to summarize everything that we've seen so far, the story so far, learning a new neural network is the process of determining the parameters of the network, the weights and the biases that are required for it to model a desired function. Now, of course, we are assuming the network has sufficient capacity to model the function to whatever precision you want. Ideally, you would optimize the network to represent the function everywhere, all over the space, but then this requires knowing the function everywhere. In practice, you won't have the function everywhere, so what we will do is draw input-output training instances from the function and estimate the network parameters to fit the input-output relationship at these specific training instances, and hope that whatever function is learned represents g of x everywhere. Right? So let's begin with a simple task. This is what we're going to do. Let's consider a classifier. Classifiers are simpler than regressions. Now, classifiers were in fact amongst the earliest problems addressed using MLPs, and specifically let's consider binary classification. There are only two classes, yes and no, right? So here is the kind of MLP that we would use. We have a network which takes in some vector of inputs and produces a value which is either 1 or 0. The network could have any structure. The individual neurons in the network are of course perceptrons. We are going to assume for now that you have threshold activations. So the perceptron, each perceptron is going to operate on a weighted combination, an affine combination of its inputs, and then this affine combination is operated on by a threshold activation. Basically, if the affine combination is positive, the output is going to be 1, otherwise it's going to be a 0 for each perceptron. And this perceptron must be trained using only training instances of input-output pairs. So now we know what a perceptron. Let's consider the simplest MLP. Let's begin with the simplest MLP. The simplest MLP has no M, it has no L, it is left with only the P, a single perceptron, right? So the single perceptron looks like so. It models a step function, right? The perceptron outputs a 1 if the affine combination is positive, 0 outside, 0 otherwise, which means there is a hyperplane where on one side of the hyperplane the perceptron produces a 0, and then on the other side it produces a 1. The boundary is linear, it's a hyperplane, and the overall function, if we were doing this for a two-dimensional input, is going to look like a step function. In every case, it's a step function in some high-dimensional space. It's a step function across some hyperplane, right? Except now this is what we want the perceptron to represent, but then when I'm trying to learn the perceptron, so suppose I want to learn a perceptron to represent a specific step function. I need to represent the step function everywhere and say, here's the step function, find me the perceptron that models this, right? Except you're not given the entire step function. All you're given is a few training samples. You're given a bunch of red dots from the region where the output of the perceptron is supposed to be 1, some blue dots from the region where the output of the perceptron is supposed to be 0, and based only on these dots, you have to learn the perceptron, which means you have to learn the weights and the bias such that the resulting step function takes the value 1 in the region of the red dots and the value 0 in the region of the blue dots, right? So now here again is the perceptron. This is the equation of the perceptron. You are looking at a weighted combination, an affine combination of inputs. The output is going to be a 1 if this is positive, non-negative, 0 otherwise, right? And so I'm going to not think of affine combinations. Linear combinations are simpler to visualize. We saw that you can convert an affine combination to a linear combination. How so? By adding an extra dimension. So for example, in 2 dimensions, if I have this line is affine. But then if I go up to 3 dimensions and I place this plane at the z equals 1 position. That's going to be this corresponding plane, correct? And the line is going to be something like so. The line actually doesn't slice the z-axis, it's affine, but when I increase the dimensions, now I can draw a plane which goes through the origin and slices that two-dimensional plane along the specific line which didn't actually go through the origin, right? And now I've converted what was an affine combination into a linear combination in a higher dimensional space. Can you turn your name tag towards me so I can wake you up? You there? You, the one who's, yes, the one with the pink cup. Can you turn the name tag towards me? You don't have a name on it, can you write it down? I make it my business to keep you awake, because I know when I sit on that side I fall asleep too. So it's not a crime to fall asleep, but then it's not very useful to fall asleep. Now, okay, so I've converted this to a linear combination, and I'm comparing the linear, and the output is now a threshold function operating on a linear combination of inputs. I did this by adding an extra component for the bias. Right? Everybody clear? And that's simply because I'm working with linear combinations, so it's easier that way. Can you write your name? And that will invoke you. So now the perceptron equation looks like this once I make it linear. There is a hyperplane through origin. Everything on one side of the hyperplane has the output 1. Everything on the other side has the output 0, right? Now, can anybody give me the equation for a hyperplane straight out without looking at the screen? What's it going to look like? So the equation for a hyperplane is going to be some, I'll use W, right? W transpose X equals 0. So why is this? Think about this. My W is some vector, right? Now, let me take any vector X which is at 90 degrees to W. Then what is the inner product between W and X going to be? Anyone? 0, right? So this guy, if I fix W, represents the set of all vectors X that are at 90 degrees to W. So a hyperplane is represented, it doesn't matter how many dimensions you're thinking about, right? So if I were doing this in 3 dimensions, then I'm going to have some vector W, and this vector W, there's this hyperplane where any vector on this plane is at 90 degrees to this guy, because this vector is going right off the plane, right? So W transpose X represents W transpose X equals 0 is the characteristic of a specific set of vectors X. That set of vectors X represents the hyperplane which is orthogonal to W. So W is the normal to the plane, right? This is the equation for a plane. Everybody gets it, right? So now let's say I have this one. So this is the plane given by W transpose X equals 0. Now I give you a vector X which is not on the plane. So I give you this X. Let me erase this one here. Yeah. This guy? So think about it this way, right? Let me use your name tag. Now this crease, so if this is the origin, this crease is clearly not going through the origin, right? So this crease is not going through the origin, which is here. I raise this off the floor. Now I can draw a slicing plane which goes through this and goes through the origin one step below. Okay. And now this crease becomes a point on that hyperplane which is actually representing a linear relationship. That make sense? Not really. Did anybody get it? Right. What happens when I raise it off? Now I can actually draw a plane which goes through that line and goes through the 0. And that makes it linear, like so. So the crease is here. So I just added an extra component. So this was x1, right? So this was x, this was y, and then I added this z, which was not there in the original equation.
So it is like it is still encompassed in the new hyperplane.
Yeah. So anyway, so let's go back to this problem. I have an x which is off the plane. What can you tell me about the distance of this x from the plane? How would you compute it? So let me tell you, right? So if this x is, I'm going to consider two cases. One case where x is in the same direction as w, because remember w is a normal to the plane, right? The other where x is on the other side of w, let's say over here. Okay? Now this is the vector that I'm interested in, but this vector can be written as the sum of this guy and this guy. So this is x. I can call this xp, which is the portion on the plane, and xo, which is orthogonal to the plane, correct? And I can say xp plus xo equals x. But then this vector which is orthogonal to the plane, that is exactly parallel to w, correct? In fact, I can write, if this distance is d, then I can write xo equals d times w over length of w. What is w over length of w? That's a unit vector in the direction of w times d, right? So I've written this like so. And so what is w transpose x? That's going to be w transpose xp plus w transpose xo, right? What is w transpose xp? Abhishek, back there, what is w transpose xp? It's 0. It's on the plane, right? So I can't see your name over there. What? Kirtiraj. So what is w transpose xo? Yeah.
The magnitude of w times the magnitude of xo.
So this is simply going to be w transpose, and we said xo was d times w over norm w, right? Which is going to be d times norm w squared over norm w. I can cancel these out. It's just d times norm w, right? So overall, when I look at if I for any point x, w transpose x is simply going to be the distance of the vector from the plane plus times the length of the vector w. Makes sense to everybody? Right, Aishwarya, makes sense? Yes or no? You didn't get it? Okay. That's okay. If it doesn't make sense to you, it makes sense to everybody, right? So again, here's what we did. I have this vector x. If I want to find the distance of the vector x from the plane, I can represent it as the sum of a vector on the plane plus a vector that's parallel to w. A vector, the w transpose, the component that's on the plane is going to be 0 because it's on the plane. So all that remains is w transpose the component that's orthogonal to the plane. And the component that's orthogonal to the plane is going to be the distance multiplied by a unit vector in the direction of w, right? So all you're left with is d. Now here, for this guy, which is in the direction of w, what is d going to be? Is it going to be positive or negative? Positive. For the other one, where d is away from w, what is d going to be? Negative, right? So in other words, w transpose x is going to be positive for vectors which are in the same direction as w. It's going to be negative for vectors which are in the opposite to w. Make sense? Right? So now that's basically the equation where what happened to my clicker. This is a standard thing. I'm going to lose my clicker all the time. Okay. Yes.
Maybe it's trivial, but why am we willing to transform from a fine to linear?
This is just a matter of convenience. right? I like to think about things. You can write this, you can explain all of this. It's much easier for me to explain the equation for a hyperplane that goes through origin than the equation for a hyperplane that is shifted from origin. That's about all it is. Right. It wouldn't make any difference, right? Yeah. So, yeah. I mean, it's exactly the same implementation, right? Anyway, so here's what we got. What we are really trying to find is a hyperplane that perfectly separates the two groups of points, which means the hyperplane must be such that all the reds are on one side, all the blues are on the other side, and specifically the normal to the hyperplane must point into the direction where you label the points as +1 and away from the direction where you label the points as -1, right? That way you ensure that W trans the sign of the inner product between the weights and the vector is positive on the one side and negative on the other side, right? And once I do that, so when I'm speaking of learning a perceptron which models this classification problem, I'm really saying find me a weights vector such that W transpose X is positive for all of the blue dots in my case, because blue is what I designated as +1, and negative for all of the red dots, right? How can I do this? Now, for this, we will invoke another very simple concept. Let's continue looking at this figure. Then suppose I give you just one vector. I give you just one vector x, and I want you to draw a plane. I'm going to label this plane as x is +1, correct? So this is +1. I want you to draw a plane such that this is guaranteed with the maximum in the most conservative way of being on the positive side of the plane. What would the best case normal to the plane be? Anyone? You guys, you don't have your name tags, right? You need one of those pages. Okay. So Jen, what would the best case normal be? It would be x itself, correct? Because if I want the plane, I want this to be on that side, I want this to be the plane. I want the normal to be x, right? So in other words, I want this to be w. W should point directly in the direction of x. Suppose I have another x, and the label that I assign to x is -1, right? For this, if I want a plane such that this is definitely on the minus side of the plane, what is the best thing I can do in terms of deciding the normal to the plane? -x, right? It's simply going to be, this would be x. So I'm going to make this my w, and that's my plane. These are the best cases for a single instance. Make sense to everybody, right? So you want the weight to always point in the direction of positive instances, away from the direction of negative instances. So here's what our perceptron classification rule is going to say, assuming again that it is possible to draw a hyperplane that separates the positives from the negatives. We are saying if you currently have a plane, then you go through the training instances, and if a positive training instance is on the wrong side of the plane, you're going to try to drag the weights vector towards the positive instance. If a negative instance is on the wrong side of the plane, you're going to try to push the weights vector exactly away from the instance. So if you have a positive class instance that's misclassified, you're going to do w equals w plus x. If it's a negative class instance, you're going to do w equals w minus x. So here is the overall algorithm. I'll actually skip the arithmetic for the algorithm, but you can see this in terms of pictures, much easier. So let's say I have those blue and red dots. It's an iterative algorithm. I randomly initialize my hyperplane. I draw some hyperplane with some normal. Okay. Now this hyperplane clearly is doing, so the blues are 1s and the reds are -1s, labels. Clearly it's misclassifying a whole bunch of reds and a whole bunch of blues. Which are the reds which are being misclassified? The ones above, right? And the blues below are being misclassified. So now I've initialized it like so. Consider this guy. I'm cycling through my instance. this is the first misclassified blue instance. So if this is misclassified and the blue is a positive, which way do I want the weight to point? Exactly at that blue, right? So here's what I will do. That's where I want the weight to point. I'm going to drag the weight towards that blue by just adding the blue to my current weight vector. And when I do that, that's my new weight. That's going to be my new plane. Sure enough, I pulled it, on the correct side of the blue, right? But then I'm not done. I have this other instance, which is a misclassified red instance, which is on the blue side, right? What do I want to do with the weight vector? I want to push it exactly in the opposite direction of the red one. So that's my red vector. I'm going to subtract it from my weights vector, like so. That's my resultant weight vector, and that's my new plane. I'm done. Now everything is correctly classified. It's a very simple algorithm. This is your perceptron classification rule. The perceptron algorithm, we have a proof that it actually converges on the website. Please take a look at it. Once you get perfect classification, everything, you're done. No more updates, right? This is great. And this, if your data can indeed be separated cleanly by a hyperplane into positive and negative instances, this algorithm is guaranteed to converge, and it's guaranteed to converge then the number of steps that it's guaranteed to converge in is proportional to the number of training instances. It's beautiful. So in fact, there's an upper bound. So suppose you have all of these training instances. You take the length of the largest training instance, the longest training instance. Now, if you start off misclassifying that guy, then you will have to correct for it, right? So because you remember, we're just adding these instances directly to the weight vector, right? And so in the process of correcting for this, I might have made a whole bunch of mistakes. So the number of steps is going to be inversely proportional, is going to be proportional to the length of the longest vector. It's going to be proportional to the square of the length of the longest vector. But then there's also this other guy. What is the best case distance of vectors from the plane? So this is to say, what is the largest distance I can find from the closest training data point to the hyperplane? This is the notion of a margin, right? Anybody who has dealt with support vector machines knows what a margin is. So the larger this margin, the quicker you can actually get to the solution. And so you're guaranteed that the algorithm will converge to a correct answer in no more than r over gamma squared, where r is the length of the longest vector, gamma is the margin. It doesn't mean that you're going to find this support vector machine. It just means that this is an upper bound on how many iterations, how many updates you will need to learn the classifier. Now this is all very fine. So what this means is that I actually give you an update rule. This was in fact Rosenblatt's original perceptron learning algorithm. I give you a provably convergent update rule which can find me the hyperplane that separates the pluses from the minuses, assuming that they can be separated. If they cannot be separated, all bets are off, and it can do so in a finite number of steps. But this is for a single perceptron. Now I give you this more complex problem. This more complex problem, we know exactly how to draw a multilayer perceptron that performs this classification task. We've seen this in lecture 2, we've seen this in lecture 1, we're seeing this again today, right? If I want to do this double pentagon, then how would I do this? Remember? Okay?
You will have multiple neurons and you will have a multiple layer perceptron.
Yes. And what do the different layers do?
The different layers will be representing the different types.
Sorry. So yeah. That's for infinite, right? Here, if I have 3 layers, it's actually much simpler than that. Yeah.
The first layer draws the 2 pentagons, and the second layer is our.
Yeah, okay. So I can actually I need 5 lines for the first pentagon. There's a next layer which composes the first pentagon. 5 lines for the second pentagon. The next layer composes the second pentagon. I can order 2. I know it's possible for me to draw a network which exactly models these decision boundaries, right? And now I give you this training data with the red dots inside the yellow region, the blue dots outside the yellow region, and I know the architecture, so I give you the perfect architecture. What has happened is that I have not told you the positions of these red dots. I have not told you the sizes of the edges and where in the space these pentagons lie. This you must figure out from the training data. So it's a very simple problem, right? Because we know it can be done. I've given you the exact architecture. And we also know exactly how to do this. I would need 5 neurons in the first layer to capture the 5 purple lines, 5 neurons in the first layer to capture the 5 black lines, the 2 neurons in the upper layers to get the 2 pentagons, and then or the lot. Except now we are only given these guys, right? Now, if I are given only these guys, if you want to find out what that first perceptron must be in the first layer, you need to learn the line that is shown on the screen. But in order to be able to learn the line that's shown on the screen using the perceptron algorithm, what would you actually require? Can you do this with these labels? Why not? They are not separable. What you really want is this. Correct? So what would you have to do to use the perceptron rule on this guy to draw this boundary? Anyone? You want to relabel the data, right? You want to go back, look at all of the dots and say, no, this blue, I want this to be a red. This blue, I want this to be a red. Only when I relabel it properly can I learn this line, right? But do you know which points to relabel? You don't, right? So how would you go about figuring out which points to relabel? You're going to have to try every possible. Did you say that? No, somebody mumbled. That was Rahul? Okay. You're going to have to try to relabel every possible instance, every possible combination. You have n training instances. How many combinations exist? 2 to the n possible combinations. You're going to have to try all of these. But is that enough? Why not? You have to do it for all of these guys, right? You're going to do this relabeling problem n times, but even that is not enough. Why not?
Why don't we have to shift it at the origin?
You could. They still don't have. You still have to relabel stuff, right? It's just a question of right. I mean, the shifting to the origin is an engineering solution. The point is about the labeling. And so not only do you have to find out how to relabel all of these guys, you have to do it differently for every one of these lines. And the only way to know whether you've done it correctly or not is because you don't really have an answer at each neuron. Where do you have the answer? At the very output. So you've got to figure out is if your relabels combine the perceptrons that you've determined with your relabeling combine to actually give you the decision boundaries that you want. Right? How much time would that take? Even if I gave you only 100 training instances, there are what, 10, 12 lines, right? So it's going to be 2 raised to 100 raised to something ridiculous. The universe would end and you'd still be solving this problem. And so although in theory you can use the perceptron learning algorithm to find all of the neurons for this network, in practice it's not computationally feasible, because if you got even one during the relabeling, if you get one sample wrongly relabeled, the whole thing is going to die, right? This is going to be exponentially hard. It's NP. So it's got exponential time complexity. It's not feasible. Yes.
You said the time will be 2 to the 100 raised to the something. How does that?
We got to do this. You have to make sure that all of them combine. So assuming that you got each of those right, then you have any number of neurons and they have to combine. It still becomes overall it's still exponential. It's ridiculous. It doesn't matter, right? Overall it's not a useful thing to be doing, right? So everybody, it makes sense to everyone. So the perceptron learning algorithm cannot directly be used to learn an NLP. There's an exponential complexity of assigning intermediate labels. And so the question is, okay, fine, this can't be done directly. Can I actually use a greedy algorithm instead? And there were algorithms called Adeline and Madeline that were proposed in the literature. We won't go over it. Take a look because these are going to feature very prominently in your quiz. Yes? Yeah. So for the standard perceptron learning rule, which is why the number of steps So if you make a mistake on one of those, you're going to have to work that much harder to recover, which is why the perceptron learning algorithm, the number of steps required by the perceptron rule depends on the square of the length of the longest vector. Right. So the story so far, learning a network is the same as learning the weights and biases to compute a target function. And while a linear decision boundary can be learned for a single perceptron, assuming that the classes are linearly separable in linear time, by the time you get to actually more complex classification boundaries, nonlinear decision boundaries, even if they can be modeled by your network, you're not going to be able to use the perceptron learning rule to learn them and get a solution in any reasonable amount of time. So that's because when you are using the MLP, the real problem here lies with the threshold activation function that we used. So with the threshold activation function, we are going to need the input-output relationship for every training instance for every boundary. And this, since we don't really have, this has to be guessed, the whole thing blows up on your face. So now the realization that training an entire MLP was a combinatorial optimization problem that can't really be solved basically meant the research in this area died for several years, over a decade, until somebody realized something very simple, right? And what is this? So consider this guy. So let's say I have my training instances which are like so, whatever, and for some reason I have drawn my decision boundary in this manner. So I'm making a mistake on one training instance. Okay. Now clearly, what do I want to do? I want to roll this guy over so that the decision boundary becomes like so, correct? But when I'm at this point, when I'm working on this decision boundary with this normal, if I move this guy a little bit in this direction, is the error going to go down? No, right? I'm using threshold functions. Simply wiggling the arrow, the plane, doesn't tell you if the error is going down or not. The only time the error goes down is if you wiggle it and wiggle it and wiggle it and it actually crosses a misclassified point, right? There is no way for you to find out whether small changes in the parameters is improving the overall classification or making it worse. And this is a problem, right? And so also when I go to the more complex problem, it's the same problem made much more complicated, in that when you got something wrong, if you begin wiggling things to find out which way to wiggle them to make things better, that's going to give you no answer at all, because the function only changes when you cross a misclassified point, right? So these things, the derivative of these functions with respect to their parameters is 0 almost everywhere, and it's extremely large at a misclassified point, right? This is not a very nice thing to be having. So there's the other problem. Real life data are rarely clean. We assume that everything is nicely separable. More likely you're going to get situations of this kind where you have a few blue dots on the red side, a few red dots on the blue side, and the whole thing gets is not going to be separable, right? So the perceptron algorithm is really not even going to work in the first place. So here's the solution. We are going to make our activation function differentiable. What this means is that we are going to change the activation function such that in a situation like this, if you currently got a boundary out here, we are going to change the activation function such that if you move it this way, it tells you something is going worse. If you move it the other way, it says you something is getting better. And if you are able to do that, then you can actually sort of begin figuring out how to shift things so that things are properly learned. And we will do that. Wow, this suddenly works. So we will do that by changing our threshold activation to something that's smoother, a sigmoid. Okay. So this means, and the sigmoid specifically is going to have this function. If you look at the sigmoid is 1 over 1 plus e raised to minus z, the sigmoid of z, and observe that it goes from 0 to 1, and it goes sort of, when z is minus infinity, then e raised to minus z is going to be e raised to plus infinity, which is very large. 1 over a large number is 0. When z is infinity, e raised to minus infinity is 0. The resulting function is 1 over 1. That's just 1, right? So it goes smoothly between 0 and 1. And if I multiply the z by some weight, I can make this steeper and steeper, and I can make it approximate the threshold function to arbitrary precision. But the nice thing is that with the sigmoid activation, it not only tells me if I'm classifying things correctly, it tells me how close I am to the exact value of 1 for every training instance. And so I can tell you that, if I change the w in this manner, am I going away from 1 or am I getting closer to 1? Am I going away from 0 or am I getting closer to 0? That information is actually presented to you, and so you can figure out which way to wiggle your parameters. So same thing when you have non-linearly separable data, right? You're going to have, or in high dimensional space, when you have the same thing. This was for the so in say 2-dimensional space, what you really, even if I'm trying to learn a perceptron for the step function, what you'll find is you have some blue dots on the red side, some red dots on the blue side. Your standard perceptron algorithm is not really going to work. If I were looking at this in 1 dimension, you have this other case that real life data are not going to be nicely separable. If my data is 1-dimensional, what is the ideal classifier? It's a threshold. Everything to the left is 0, everything to the right is 1, and the problem, of course, is you're going to get data of this kind where you can't really find a threshold, right? So here's another situation where your sigmoid actually gives you something useful. And what is that? The sigmoid not only gives you an idea of how far away you are from 1, it gives you some extra information that you can use. Now look at data of this kind. Clearly I cannot build a classifier, right? But then let's change my perspective. For each position x, let me begin looking at a small region around that x and see what fraction of the instances in that small region take the value 0. And so if I take the value 1. So out to the extreme left, the fraction of instances that take the value 1 is 0. As I begin moving from left to right, the fraction of instances that take the value 1 keeps increasing. And it keeps increasing and increasing. Eventually, you're going to get to a point where all of the values take the value 1. And so the fraction of instances that take the value 1 is going to be 1. Now those blue dots, they actually represent the probability that you will encounter a 1 when x takes that value. So this curve represents the a posteriori probability of 1 given x. So it has a nice interpretation. The sigmoid has a probabilistic interpretation which says that what is the probability of 1 for any given x, and it naturally follows, right, that as you go from the left to the right, you expect to see this nice smooth curve. It's well modeled by a sigmoid. Now this has been the case of a 1-dimensional variable. For 2-dimensional variables, you'd have 2 dimensions, and the sigmoid is going to be this folding sheet which has the same characteristic. It's still a linear classifier. Why is it a linear classifier? It's linear because if I slice the sigmoid at any height, that edge that you get for the slice is going to be a hyperplane. So if I say I'm going to slice the sigmoid at sigmoid value equals 0.5, that slice is going to be a hyperplane. So it's a linear classifier. Anyway, we'll return to this whole business of probabilities in a later class. Just wanted to show something extra that comes with sigmoids, but then let's move on. What we did was to replace our activation function with something that was differentiable. So this means this guy here is differentiable. If sigma of z is differentiable, what this really means is that I can tell you for small changes in z, how does y change? That's what differentiability really means, right? But then z in turn is an affine combination of the weights and the inputs. For affine combinations, we already know how much does a small change of x result in a small change of z, and how much does a small change of w result in a small change of z. So I can chain these and say, a small change of w results in the small change of z, but a small change of z results in the small change of y. Therefore, a small change of w results in the small change of y. You can actually chain the whole thing, and you can compute a derivative of the output with respect to every one of the inputs and every one of the parameters. And so this means that you can compute a change in the output for a small change in your parameters, which basically solves this problem, right? Now that's for a single perceptron, but then when I connect these perceptrons into a network, the same thing still holds, because for each perceptron I can tell you how much a small change of input or parameter really affects the output. So now consider this network. If I take this edge, for instance, for this edge I can tell you how much a small change in the weight of that edge is going to modify the output of this perceptron. But then once I can also tell you how much a small change of the output here is going to affect these two y's. I can also tell you how much a small change of those y's is going to affect the overall output, which means I can combine all of these to tell you how much a small change of this w is going to affect the y, which means now I know how to change that w in order to make the entire function shift towards something that's more acceptable to me, where the error goes down, right? This is how I can actually go and inspect every single variable in my network and figure out whether a small change in that parameter is actually going to modify my network in a manner that improves its accuracy or makes it worse. So this overall network, which is a function, is now differentiable. If the activations are differentiable, then the overall network becomes differentiable with respect to every one of these parameters, which means now of course that how exactly we'll compute these derivatives we'll see in a later class, but it means we can compute the derivatives. So this changes the overall setting for learning our MLP, right? Given now we are still at the same situation here, given a set of training instances which are XD pairs, input output combinations. We have a collection of these guys and we are going to use this collection to find the network parameters. We are assuming that the architecture is specified by us. And as a quick recap, what we are really going to do, what we really want to do is to find the network parameters which minimize this error, right? If this is the current output of the network and if this is the function you want to model, you want to minimize the error between the two, the area of the area of the error region. But then we're going to make one small change in that it's not really important for you to minimize the error everywhere. So consider this, that for whatever data you're working on, the data never really comes out here. You're never going to see data from this region. Does it matter that you reduce the error over there? It doesn't make any difference, because whether you make an error there or not is irrelevant. You're never going to see data from that region, right? So in other words, you want to focus more on regions where you see more data, and you want to give less importance to regions where you see less data. So instead of just trying to minimize the error, you will minimize a weighted error, where for each x you will apply a weight which is the probability of that x. So this is the actual error. This is the actual error function that you're going to minimize with respect to w. But what is this function? This is just the expectation of the divergence, right? P of x is the probability of x. So this is the expectation of the divergence. And so we are going to minimize the expectation of the divergence. This is what we really want to do. What we really want to do is to find the w's that minimizes the expected divergence between the output of the network and the actual function, right? In reality, you don't have the function everywhere. You just have a bunch of samples, bunch of input output pairs. So what we will do instead is, you don't actually have the function specified everywhere. You just have these guys. So that means for each of these guys, I can compute this length, right? I can compute the length of the error between the actual output of the network and the desired output of the desired function value at every one of these training instances. And I can just focus on minimizing those lengths, the sum of those lengths, which is to say, I'm going to minimize the average error, the average length of those error lines over all of my training instances. And if I do so, I can make sure that my function actually fits the input output relations at the points that I do have, and I'm going to hope that it works everywhere else. Make sense? Yes. Px is the probability of x. You don't really know, right? The point is that here is the thing. Hypothetically, you want to minimize the error, but you want to impose more importance to regions where x is more common and less importance to where x is less common, right? So that is, so you really want to minimize the weighted error, but then in practice you're not actually going to have p of x. What you're going to have is samples of p of x. But if you're sampling p of x, you will naturally just get more samples where x is more common and fewer samples where x is less common, because you're drawing from real life, and real life really just has a natural distribution. You're actually going to be sampling from p of x, right? So in other words, these samples are actually going to be drawn from p of x, even if you don't really know p of x. Okay, but our point is this: this guy over here is an empirical estimate of the actual loss, the actual error that we are trying to minimize. Okay, so this function on top, which is the expected divergence, is what we would like to minimize. That's what we will call our risk, or this is the, there's a lot of terminology that flies around, so I just have the terminology on the slides. Later on we'll get rid of this altogether, right? So this is the error that this is the divergence that we're trying to minimize, right? But then we can't really compute it. What we will get instead is this average error across all of the samples that we've drawn, and this is what we will call our empirical risk. So this is an approximation to the guy on top, and you can show that in expectation the two have the same value, right, on average. But and we'll deal with that in a later lecture. So instead of minimizing this guy, you're going to be minimizing this term at the bottom, because the term at the bottom is your best guess for the term on the top. And so what we actually perform is empirical risk minimization. We minimize the empirical risk computed over all of your training samples, the samples that you've drawn, and this empirical risk, which is the weighted, which is the average of the divergences computed at every training instance, is also called the loss. And so this loss is what we will minimize, and the weights, the parameters that we will compute for the network, are the parameters that minimize this loss, which is simply the empirical risk computed at the samples that we do have. Although keep in mind, in theory what you really want is to minimize that entire area, not just the sum of the lines, right? The sum of the lengths of the lines is simply your best guess or your best proxy for the area, and that's what you're going to minimize. Make sense to everybody, right? And so here's the overall, this loss is really a measure of error. Using standard terminology we're going to call it a loss, but again keep in mind this is just a measure of the error. Okay, so here's the problem statement again. You're going to have a collection of input-output pairs. These are your training data. Over the collection of input-output pairs, you'll compute a loss, which is the average divergence between what the network actually computes at the x and what you want it to compute. This average divergence is what you call the loss, and we are going to try to minimize this loss is a function of the parameters of the network. You change the parameters, the loss is going to change, and this loss is what you're going to minimize. So this is a problem of function minimization, which is an instance of optimization, right? So the story so far, we learn network parameters by fitting networks, by fitting them to training instances drawn from a target function. Learning networks of threshold activation perceptrons requires solving a hard combinatorial optimization problem, so that's not what we will do. Instead we use continuous activation functions with non-zero derivatives, so that enables us to figure out whether we are improving things or making things worse when we wiggle our parameters. And specifically the logistic activation function, which is the sigmoid, actually computes the a posteriori probability of the output given the input. Now here's something else that I forgot to mention. This is very important. This divergence function, we said that the activation must be differentiable, right? Is that enough? Making the activation differentiable tells you how much a small change in the parameter or the input changes the output. That's not enough, because if the error that you compute is not differentiable, right? Even if the y changes a little bit, if my error only changes every time I cross a training point, then the error function is not differentiable. So I will not be able to tell you whether a small change in the parameters is modifying, improving, or worsening the error. So the divergence function that you compute must also be differentiable, which means that you want to be able to say, if I change this w by 10 raised to minus 6, is my error going down or going up, right? That means that error function, the divergence function, must be differentiable. It's not enough just for the network to be differentiable, even the divergence must be differentiable. And so we define a differentiable divergence between the output of the network and what you really want the output of the network to be. And the total error is the average divergence over all of your training samples. And we are going to optimize the network parameters to minimize this total error, which is the average divergence over all of your training samples, something that we'll also call the loss. Now the nice thing about the manner in which we set up all of this is that end to end everything is differentiable, which means that when I can tell you how much a small change in any of my parameters affects the output of the network. I can tell you how much a small change in any of my parameters affects the error between what the network computes and what I want it to compute. And so now I can begin wiggling my parameters to reduce that error. Make sense? Right? So this is a problem of function optimization. Now I have at this point a half-hour spiel on function optimization, which I will compress to about 8 minutes, and then we'll go over the rest of it again in the next class. First thing, a brief note on derivatives, right? I keep using this term derivatives. How many of you have done calculus in college? Right. So someone there, you at the very back who I can barely see. Right there, yes. So what is a derivative? It's how much a small change in one variable affects the output, but it's not, there's something even more very specific than that, okay? So maybe this gentleman at the very back leaning against the wall. So how do you define a derivative? It's a rate of change. It's beautiful, right? So here's what we are really speaking of. Here's the only way to think about a derivative. Anything else is going to break your heart, right? And give you bad marks in some problem or the other somewhere in life if you continue taking exams. So suppose I have a function y of some function x, then a derivative at any x tells me is a multiplier that multiplies a small change in x to give me the corresponding small change in y. So at any x, I can say, what should I multiply a little change delta x by such that the result gives me the change in the function y. That is the only way to define a derivative, right? So for scalar functions, if I say y equals f of x, you're saying if I change my x by a little bit by delta x, this results in a small change delta y. So what do I multiply this delta x by to compute this delta y? That multiplicative term is your derivative, right? Now we do something horrible in life, and they teach us something really bad in school, which is you write this as dy over dx, right? What could go wrong? You think of it as a fraction. It's not a fraction, right? What if x is a vector? When's the last time any of you divided something by a vector? I hope the next time doesn't happen, but if it does, it's the first time, right? Anyway, so we like to write f prime of x for the derivative. That's a much more reasonable thing to be doing, right? Because f prime of x sort of encapsulates the spirit. Now, see how this translates. This notion translates to vectors. So let's say I have a vector function, scalar function of a vector variable. So y equals f of x, where x is now a vector, right? I can still ask this result. Now what is a delta x going to be in this case? Delta x is also going to be a vector. correct? And I can still ask you, what is this term alpha that I must multiply a delta x by to get a corresponding delta y, right? And that is going to be my derivative. Now delta x is a vector. If my x is a column vector, delta x is a column vector. What is the shape of alpha? It's got to be a, is it a vector matrix? Are you sure? Y is a scalar. Y is a scalar, right? It's got to be a row vector, right? Alpha must be a row vector, otherwise these two are not going to multiply and give you a scalar. So alpha is going to have this form, alpha 1 through alpha d, and delta y is going to be alpha 1 times delta x1 plus alpha 2 times delta x2 and so on, component wise sum, right? Product and sum. Now because delta x is a vector, I can sort of generate delta x in many different ways, right? So what is this alpha 1? Alpha 1 tells you how much y changes when I change only x1 and don't change the other things, right? If delta x2 through delta xd are all 0, then alpha 1 tells you how much y will change if I just change the first component. It's the partial derivative of y with respect to x1, right? Where you fix everything and modify only x1. So alpha 1 is often going to be called dou y over dou x, which basically says how much will y change if I change only x1 and I don't change the rest of it. And this vector is going to be the vector of partial derivatives. Clear to everybody, right? So we will often represent this using this inverse nabla, the inverse triangle. The subscript tells you the variable that you're taking the derivative with respect to, and it's going to be the vector of partial derivatives. Now you often encounter this term a gradient. A gradient in all the math you've ever seen is going to be a column vector. Technically, using this notation, the gradient is the transpose of your derivative. Just be very sure, right? So now I'm going to just sort of, I don't have time to go through the rest of this, but I will go a bit to what a derivative of multivariate variables functions means, right? Consider a function of multiple variables. Again, I can still write df equals the derivative times dx, right? This equation is correct. I'm not writing it as a fraction. Obviously, I cannot divide by d of x. Writing 1 over d of x is going to be, they'd fail me as a professor and send me home if I wrote that. So because it's a vector, you can't divide by a vector. But this equation is right. And what do we know about, nabla of f? It's a row vector, right? And what are the components of this row vector? They're all the partial derivatives, right? This entire term is an inner product, right? So I can say df is an inner product of the derivative and dx, right? There's a very specific behavior that the inner products have. Suppose I take two vectors. What is the inner product? Let's say both vectors are unit length. What is the inner product between these two vectors? Cosine of the angle between the vectors, correct? When is it going to be maximum? When they are both pointing in the same direction. So suppose I go back here to this guy. Suppose I go to this guy, right? Now the derivative nabla f, that's fixed. That's a characteristic of the function. The only thing that you can vary is delta x, right? So let's say I keep the length of delta x fixed and I keep changing delta x and rotating it around. When will this inner product be maximum? When delta x is pointing exactly in the same direction as the derivative, correct? That's when the cosine is going to be maximum. So in other words, this derivative, the function f increases most rapidly if delta x is going to be in the direction of the derivative. If I move delta x away from the direction of the derivative, the corresponding delta y, delta f, is going to decrease. right, because the inner product decreases. Make sense to everyone? So in other words, the derivative of a function of a vector, which is basically the gradient transpose of the gradient, points in the direction of the fastest increase of the function, and the negative of the derivative points in the direction of the fastest decrease of the function. And we're going to use all of this in the next class. We'll stop right here. Right. Look through the slides anyway, because even if I haven't covered topics, it's going to appear in the quiz. Thank you.